polynomial. All right, a polynomial function is what we are now concerned with. And as a matter of fact, we have been looking at a number of examples of polynomial functions. We haven't been calling them that because they do have their own names. However, if we were to look at a linear function, what's our formula, by the way, that we have been writing for a linear function? And Ron says
y equals mx plus b.
y is equal to mx plus b is a formula for our linear function. In fact, I would like to put a function in front of this one, if I may, in which I will call this one number 2, and I would like to mention a constant function. And you'll see why in a minute, why I decided to put a constant function first. What is our formula that we have indicated, Bob, for a constant function?
Y equals b.
Simply y is equal to b, all right? And then in yesterday's lesson, we were looking at a quadratic function in which the pattern, if you recall, was what? Y is equal to, and Todd says?
ax squared.
Ax squared
Plus bx.
plus bx
Plus c.
plus c, where a cannot be 0. And remember the reason why a cannot be 0? Well, if a were 0, then in fact you would be back to a linear function of the pattern bx plus c, where b is really m and c is really b. Okay? Now, after a quadratic function, perhaps another polynomial function that one might look at is what we would call a cubic function. All right? Now, we're not going to do very much with the general case of the cubic function as we did, say, with a quadratic function. But let me simply write down a pattern which would generate a cubic function, all right? The general case of the cubic function, in which, notice now, it would be ax cubed, all right, plus a bx squared plus cx plus d, where, of course, what number cannot be 0? In this case, Brenda? A cannot be 0, because if a were 0, then you would no longer have a cubic function, but you'd be back to the case of a quadratic, okay? Now, after the word cubic, we lose track of our polynomial functions a little bit in terms of some words that we use to describe those functions. Some people refer to the next case as a quatric function. But in fact, the word that one might use is a polynomial function of the 4th degree, okay? A polynomial function of the 4th degree. Let me simply indicate that. And I don't think I even want to write down the formula for it, but it would indeed be the same case of ax to the 4th plus bx cubed plus cx squared plus dx plus e, and so on. All right, you can have a polynomial function of the 100th degree if you want. But what happens is that one changes the notation after a while. By the way, let's come back. In fact, let's think of this in reverse order. What is the degree of this polynomial function, this cubic function? What degree is it? And what do you think? Well, what if we didn't have a function here but simply this expression, what degree did we give that polynomial expression when we originally talked about it, Chuck? It would be of the 3rd degree, all right? In fact, the degree of the polynomial here determines the degree of that function. And let's look then at this this quadratic function. What degree would it be? And of course, Steve says
2.
Of the 2nd degree, and the linear function is of what? Is of the, Mary Lou?
1.
Of the 1st degree. And in fact, we had defined way back when a constant function of degree what? Of degree 0. And every constant function except 0 itself, and we said that one has no degree, okay? Now, what I'd like to do today is to concentrate more on this cubic function. Perhaps we'll get into a little bit with the 4th degree polynomial function, all right? Let's turn to a coordinate system, and let's look at the function f of x equals x cubed, a very simple little case of simply a is 1 times x cubed, okay, where all of the other constants are 0. B is 0, and c and d are 0, okay? Now let's see if we can't make the graph of this function. Notice I changed the notation here to read f of x is equal to x cubed, just so that we get accustomed to seeing both. Well, again, let's plot a number of points and see what the graph will look like, okay? And an easy point to select for x is what? An easy number to take is, what? 0. And if x is 0, y must be what? 0. F of 0 is 0. If x is 1, 1 cubed is 1, and f of 1 then is 1. Okay, so we come out 1, f of 1 must be 1. And in fact, let's decide to take a negative 1 for x, okay? If x is negative 1 cubed is what? Negative 1. So f of negative 1 equals negative 1. Is that right? So negative 1 comma negative 1 must be on our graph. Oh, let's now take x is 2. If x is 2, 2 cubed is 8. So f of 2 equals 8. All right, so here's 2, 1, 2, 3, 4, 5, 6, 7, 8. And notice our graph goes up rather quickly. Now, if x is negative 2, negative 2 cubed is negative 8. So f of negative 2 is negative 8. 1, 2, 3, 4, 5, 6, 7, 8 in a negative sense. And notice now we have these points in which if we would have took a value, say, of x to be 1/2 cubed is what? Is 1/8. So that point might be somewhere in here. Now if I were to try to make a rather smooth curve through these points, I think you would agree that it would come on down through here, and now it would have to have a rather sharp bend through here, and then continue on in this fashion, and go on forever like this. And in fact, this shape that we have here is what we may think of as a cubic curve, all right, in which we have this bit of a bend that we see here in this graph, okay? Let's go on and look at another example, and in this case, notice we have on the graph the function f of x is equal to 1/8 x cubed. It's really the same function as we had in example 1, but I included a constant of 1/8, all right? Now, for example, if x is 1, all right, we have there the number 1/8, and so you see it right here. If x is 2, 2 cubed is 8, and 1/8 of 8 is 1, so when x is 2, y must be 1, all right? Now, when x is 3, we end up with a number here. When x is 4, we end up with a number here. Now, when x is negative 1 cubed is a negative 1, and 1/8 times negative 1 is a negative 1/8, and so on. And notice then that the curve is going to look like this. Is that right? Okay? Now, what I'd like us to do is to investigate the case of f of x is equal to the opposite of 1/8 times x cubed. All right? Now, from what we did yesterday with the quadratic function, what was the effect of that number, the coefficient to be negative? The opposite of x squared did what to the graph, Chuck?
It shows that like your 0 point would be the maximum or the minimum.
All right, yes, the 0 point was going to be either then the max or the min, but there was another characteristic that occurred as a result of that number negative 1. And can anybody think of that, Brenda? It turned it upside down, so to speak. Is that right? In other words, it was symmetric about what? About what axis did that then occur? And Brenda? Well, the axis of symmetry was a result of the fact that it was an x squared, the 2 factor there. So, Steve?
The y-axis.
It was, well, that would be the same, I think. The y-axis would be the axis of symmetry this way. Brenda? The x-axis, I think, was our axis of symmetry. For example, y equals x squared, which looked like that. Y equals the opposite of x squared, write it over in this case. Is that right? Now, let's see what effect this negative sign has on a cubic, okay? And let's look then at what we have here and simply indicate it by the opposite of that, all right? Now, think of these f of x values. Think of those y values. In this case, instead of it being up here at positive 1, when we come out here 2, what should it be? It should be down at what? At negative 1. So I think you'll agree that this point should be on our new graph of the opposite of 1/8 x cubed. If this point here is, say, at 1, 2, 3 and a third or so, it then should be where? Where? Negative 1, 2, 3 and a third. Is that right? All right. Now, if this point is out here at where? We're up at this point, which is at 1, 2, 3, 4, 5, 6, 7, 8. So what then should our coordinate be here? We have 1, 2, 3, 4, comma, negative 8. 1, 2, 3, 4, 5, 6, 7, 8. And this point should be on our graph. Is that right? Similarly, on this side, notice, of course, this point would be right about here. And on this negative side, when we take the opposite of this, it's going to then make it positive. Is that right? So I think you'll agree that this point would have its mirror image, say, at about this point. And we would have this point on our new graph. And this is where 1, 2, 3, and some. 1, 2, 3, and some is right about in there. And then, of course, here we have what? At negative 8, so then we want to be up at positive 8. Is that right? Now, through those points, I think we can make a nice smooth curve. and it will look something like this, all right, through the origin. Notice it's a bit more flat as you get close to the origin because of that factor 1/8. All right, and the graph then of the opposite of 1/8 x cubed is going to be this curve that we have here, okay? Now, again, notice it's a flip around the x-axis. The opposite here creates that change in our graph, which is going to reverse it around the x-axis, okay? Let's look at a third example. And here we have a situation in which we have x cubed minus 4x. And notice now we have this second term here of 4x, a minus 4x, in which a happens to be 1 here, and then b is what number?
Negative 4.
-4, all right? Now let's think of this in terms of, let's factor out the number x, all right? And if we were to factor out an x, what's left? X squared minus 4. And what do you know about x squared minus 4? It factors into, Ken?
X plus 2 times x minus.
An x plus 2 times an x minus 2, okay? Now, let's look at this function, and let me ask, what are the zeros of this function? And Steve says?
-2 and 2.
-2 and 2 and 0, okay? In fact, notice now we have 3 zeros of this function. All right, so here then is going to be one point at -2, comma 0, at 0, comma 0, and at 2, comma 0 are 3 zeros of the function. Okay? Now, let's look at this equation as we have it written here. Now, if x, say, were -10, -10 cubed is going to be what? A positive number or a negative number?
Negative.
A negative number. So it's going to be way down here somewhere. Is that right? Okay? Now, as x increases from left to right, all right, as x increases from left to right, let's see what's happening to our graph. All right? If x is, say, -10, we're way down there. And as x becomes, say, -5, y value begins to come up. Is that right? Okay? And then finally, right here, when x is -2, you are at 0. And then it looks like it's going to have to turn and then pass through here in order to be able to have another 0 at the origin. And then it's going to come down somewhat, and then it's going to have to turn again and then continue on up. Is that right? Now, for example, if x, say, is +5, 5 cubed is quite big. Is that right? So let's now pick out some other numbers, some other values for x, and see exactly where we are. But I went through that kind of a description so that we have some idea of what the graph is going to look like before we actually plot it, okay? Well, let's take a value of x to be, say, 1. And if x is 1, 1 cubed is 1 minus 4 is -3. Is that right? So when x is 1, we're down there at 1, 2, 3, and sure enough, that's just about what we would have hoped for. Is that right? Now, if x, say, is -1, -1 cubed is -1 minus 4 times a -1 is +4. -1 plus 4 is up at where? Up at +3. Is that right? So when x is -1, we're up at 1, 2, 3, and this point must be on our graph. Now, let's just take a number, say x is -3. All right, now if x is -3 cubed is -27 plus 12. And -27 plus 12 is -15. Is that right? So when x is -3, we're way down here off of our graph. Okay? So I think you will agree that as we come up here from this number, our graph is going to come up here, and then it's going to come up through this point, It looks like we might have a what we might think of as a turning point up there. It's going to have to come through this point and then continue on up in this fashion like this, and this is then going to be the graph of this cubic. Okay? And notice the general shape of a cubic is always going to be one that has a bit of a wiggle in it. Sometimes the wiggle is much sharper than in other cases. All right? Let's look at another example. In this case, notice we have 4x minus x cubed. Now, again, let's do what we did in example 3, in which if we were to factor out the number x, all right, if we were to take out an x, we have left what? 4 minus x squared. And what can we do with 4 minus x squared? That factors into what? And Ken says?
2 plus x times 2 minus x.
All right, a 2 plus x times a 2 minus x. Now, notice in this case that, in fact, perhaps I should have rewritten it. Let me do so up here. Y then is equal to the opposite of x cubed plus 4x. And notice now that the coefficient of the highest term here, the x cubed term, happens to be negative 1. Is that right? So let's come back here and look at our graph in example 3, and keeping in mind what we have there in example 4, which is the opposite of x cubed plus 4x, what do you think the effect of in example 4 is going to be on the graph of example 3? What do you think it's going to do? Just that same idea as we did before. Chuck?
Well, it'll like turn it around and opposite, so like the arrow going down this side now will be going up.
All right. And one word which is going to describe that. One word. David?
It'll reverse.
It will reverse it about what?
The x-axis.
About the, Ron?
X-axis.
About the x-axis. Is that right? In other words, it's going to take this graph. Again, what we're doing is taking the opposite value of y, aren't we? So the opposite of value of y is going to have the effect of flipping this graph about the x-axis. Is that right? Okay. Now let's come over here and look at example 4. Where are the zeros of this function? Where are the zeros? Well, at what number here? 0 and at negative 2 and at 2. Okay. Are those the same zeros from example 3?
Yes.
Yes. All right. Now they're the same. Now let's now come back here and look at our equation, which is in this pattern. If x, say, is negative 10, negative 10 cubed is what? Positive or negative?
Positive.
Negative 10 cubed is where? Is way down there, right? But now the opposite of negative 10 cubed makes it what? Way up there. Is that right? It makes it positive. So our graph is going to have to start from, right, from way up here somewhere. It's got to do its thing and then end up in the lower right-hand corner. Is that right? Okay. In other words, we say that the graph ends up, it is decreasing as x goes from left to right. The graph decreases as x moves from left to right. Does everyone understand that description? All right, the graph is going to decrease as x moves from left to right. Now, well, with that kind of an idea, let's actually graph a few of these points. Now let's again take x, say, to be negative 1, and let's now pick out, say, this pattern up here. If x is negative 1 cubed is negative 1, and the opposite of negative 1 is 1, minus 3 is 1, minus 4 is a number at what? Negative 3. So when x is negative 1, y must be negative 3. When x is positive 1, what must y be?
3.
Positive 3. 1, 2, 3. Does everyone agree with that? And remember now, when x was what? Negative 3, y is going to be up here at, what was our number? At 15. Is that right? So our graph is going to start out from up here. It's going to come on down through this 0. It's then going to have a turning point. It's got to come through the origin here. It's going to have another point here, and then it's going to go through this point and continue on down in this fashion. Okay? And now notice, it started from the upper left-hand corner, so to speak, of our second quadrant, and it ends up down here in the lower quadrant, the fourth quadrant. Okay? Let's look at a fifth example. And notice now in this case, what I have here on a dotted line, the graph of 1/8 x cubed again. And now what I want to do is to investigate what happens if we were to add or subtract a constant. Okay? Now, in the fact that we have here minus 4 from 1/8 x cubed, what is the net effect of subtracting 4 from the y value? Just think of it that way. What would be the net effect of that with respect to the graph of 1/8 x cubed as we have it here? Todd?
Move it down 4 spaces.
It's going to move this graph down 4 spaces. Does everyone see that? All right. In other words, if we didn't have that negative 4 there, when x is 0, 1/8 of 0 is 0, and from this point, subtract 4. So Todd says, all right, well, if we come down 4, this point, instead of being up at the origin, is now going to be here. Is that right? When x, say, is 2, 1/8 of x cubed, of 2 cubed is up at 1. Instead of being at 1, it's going to be 4 places below that. 1, 2, 3, 4. Is that right? And so all we need to do is to move these points 4 points down. Is that right? 4 units down. 1, 2, 3, 4, which is at this point. And now here we have a point on which if we move it 1, 2, 3, 4 units down is right here. Is that right? Now, let's continue on this side. We now want to move this point down 4 units. And so we have 1, 2, 3, 4, is that right? Right in here. And then I think we had a point right in there. And now let's move this point down 4 units. 1, 2, 3, 4. And then 1, 2, 3, 4. And I think that's sufficient for us then to get some idea of what that graph looks like. And if I were to make a nice smooth curve through those points, I think you would agree that it's going to look like that. Okay? And so this then is the effect of having a constant. Now, of course, if we had, what, 1/8 x cubed plus 4, what would its effect be on the graph of the original one? And Sally says
Everything would move up.
it would move up 4, and what your graph then would end up on the top side of that. Okay? So when you go about, notice we're just sketching these graphs. We're not interested in plotting 1,000 points or so and trying to draw a smooth curve through all of those points. But if you have a little bit of this insight into these graphs, I think it makes for a meaningful experience. Okay? Now let's look at a sixth example here, and notice we have two graphs on this coordinate system. And what I'm really interested in here is the graph of 1/4 x to the 4th power. And if I simply graph 1/4 x to the 4th power, which is this graph right in here, all right, you wouldn't have the feeling for what that graph looks like unless you had something to compare it with. And if you remember yesterday, we looked at a graph such as 1/4 x squared. And if you then were to graph 1/4 x squared on this coordinate system, it would be this one that we have here. And notice 1/4 x to the 4th still has this shape. That is, it's going to continue on up in this direction, which we have an axis of symmetry, but it's much more steep. And notice right down here, you can't see it too well on my picture, but as x approaches 0, that is, if it's between 0 and 1, I think you will have to agree that what? The graph of a number such as 1.1 to the 4th power is much, much smaller, isn't it, than 0.1 to the 2 power. Is that right? So the value of x to the 4th power right in here between 0 and 1 is going to be below the 1 of x squared. Okay? And I think that's all that we need to say about this example. Let's come down here and look at another example in which, notice now, we have our function written in terms of the factors. Our formula for the function is written in terms of factors. X plus 2 times x minus 6 times x minus 3. Now, if you were to multiply these out, all right, what would be the degree of this polynomial? What is its degree? And Ron says of the 3rd degree. Is that right? So indeed we're concerned with one of these cubics, just as what we have been doing. Now, is the coefficient of this first term, of that cubic term, is it going to be a positive number or a negative number? All right, it's what? Here we have what? X times x times x, and when you multiply all that out, its coefficient is going to be what number? It's going to be what? X cubed. Yes, but what's the coefficient? In front of x cubed, Brenda says it's 1. All right? Now, remember the general shape of the cubic in which that coefficient was 1. Is our graph going to increase from left to right, or is it going to decrease from left to right? What general pattern are we looking at? Is it going to do what, Chip? It's going to increase from left to right. Is that right? Okay? Does everybody see that? All right? Now, where are the zeros of this function? What are the zeros? Well, 1 0 here is at negative 2. All right? Negative 2 comma 0. Another 0 here is at 6, and another 0 at 3. So 1, 2, 3, and then 4, 5, 6. These are the zeros of our function. Is that right? Okay? Now, I think you all will agree that our graph has got to come up here through this point. All right? Do something. Come on back down through this point, and then continue on up in that fashion. Now, I'm not really too concerned at this point, at this stage of the game, how high this graph comes or how low it goes, all right? And we can investigate that. You can investigate that as you go along in your mathematics. But right now, I'm more interested in your being able to simply make this sketch, okay? So, in fact, let's see now. If we were to substitute x as 0, this will give you some idea of how high the graph will go. If x is 0, we have 2 times a negative 6 times a negative 3 is way up at what number? At what? Up at 36. Is that right? So when x is 0, you're way up at 36, which is off of our graph. So let me distort this graph somewhat and have the graph come up through this point here, okay? And have it go on up through there somewhere. It's going to have to come through here. I don't know how low it goes. And then it's going to have to come up through that point and continue on forever in that fashion. All right? And here's what we think of as a sketch of this function as represented by this formula here. Okay? Let's look at an eighth example, in which notice here we have the opposite of x minus 2 times x plus 4 times x minus 5. Now, if you were to multiply this all out, you're going to have x times x, which is x cubed, but then you have this dash symbol in front. So, if the coefficient of that x cubed term is what number? In this case, it is what number? Negative 1. What is our graph going to do? Is it going to increase from left to right? Or is it going to do what? Steve? It's going to decrease from left to right, all right? In which it's going to have to do something like that. Everyone agree with that? Now, let's look for those zeros again. And here we see a 0 at 2. All right. And x plus 4 gives us a 0 at where? Negative 1, 2, 3, 4 at negative 4. And a 2 and another 0 at 3, 4, 5. And there are 3 zeros. And we all agree that our graph is going to have to do what? Is it going to decrease from left to right? Is that right? So, you say, all right, it's going to have to start from up here and come on down through that point. It's going to intersect through that point. It's got to turn around somewhere, go through that point. I don't know how high it's going to go. It's got to turn around and go through that point and continue on forever in that direction. Okay? Well, let me do one last little idea here, and I think that that's all that we need to do for today. Notice in this graph, for example, right here, say, let's say at negative 1. When x is negative 1, y is what? It certainly is y. Is it positive or negative? It certainly is negative, isn't it? All right, let me use our function notation. So f of negative 1, in this case, is less than 0, isn't it? All right? Now, right here, say at this point, 1, 2, 3, when x is 3, f of 3 is going to be what? It's going to be up here somewhere, which is what? Is positive. Is that right? All right. So f of 3 is going to be greater than 0. Well, let's look for some number. Let me decide to call it c, where c must be between where and where? Between negative 1 and 3. Is that right? There must be some number between negative 1 and 3 such that f of that number must be 0. Is that right? In other words, here our graph is below the x-axis, and here our graph is above the x-axis, and if we have a nice smooth curve there, which is what we were assuming that we have, what must happen? Somewhere between those 2 points, the graph has got to do what? It's got to do what? It must cross the x-axis. Is that right? So what we can say is that there must be some number c such that f of c is equal to what? Is equal to 0. All right? And in fact, in our picture, as we see it here, what number must c be? C has to be what number? C has to be, Ron?
2.
It has to be 2. C in our case has to be 2. Now what this idea says, what this theorem, actually it's a theorem which we're not going to prove, says is that there is at least one c in there. In the case that we have here, I think that that's all that we will have, is just that one number c. Okay? Well, let me give you your assignment for next time, and I think that's all that we need to do for today. This will be assignment